Hello, everybody. Welcome to today's session about feature engineering with Hamilton. Here we are today. Today's speaker is Stefan Krasovs. He's the CEO of DAGWorks-Inc. Stefan is the author of the popular open source framework called Hamilton, and he has been a guest lecturer at Stanford Machine Learning Systems Design course. He spent over 15 years working across multiple parts of the stack. For the last decade, he has focused primarily on data, machine learning related systems, and their connection to building product applications. He has built many 0 to 1 and 1 to 3 versions of these systems at places like Stanford, Honda Research, LinkedIn, Nextdoor, Idibun, and Stitch Fix. Wow, wonderful. We are delighted to be part of the session, and the stage is all yours, Stefan. Over to you.
Thank you. Let me just share my screen. And let me see, chat window. Cool. Hi everyone. Thanks for having me. Yeah, my name's Stefan Krafchik, CEO of a company called DAGWorks, DAG for Directed Acyclic Graph. And I'm excited to talk to you about an open source project I kind of created at Stitch Fix before I started the company DAGWorks, and going to be talking about feature engineering. Do feel free to put questions in the QA and chat, and so I'll try to if I don't see them, I'll things will be flagged to me. But otherwise, if my accent is a problem or I'm going too quickly, do feel free to stop and pause and ask questions. In terms of just a little bit more about myself, I've been in Silicon Valley since 2007, so I've been here a while. I've been at a various bunch of companies. In terms of where I created Hamilton, and a lot of kind of my learnings in terms of helping get production or things from prototype to production for data or machine learning purposes was at a company called Stitch Fix. For those who don't know, Stitch Fix was famous for having over 100 data scientists, and so I was engineering for data science for them. And so in which case this is where I created the open source project Hamilton, was to help a particular team there. In terms of, just to give you a bit of a mindset for this talk, so I'm going to do a quick high level overview just to kind of frame some of the positioning, right, in kind of 5 slides, and then I'm going to talk about actually get into the talk. Some of the primary motivations for me in terms of building out Hamilton and then therefore applying it to kind of feature engineering was kind of it can be represented in the 2 sides of this slide here. So imagine you are coming into some sort of project and you're inheriting some sort of code. 1% of it looks like this, or the alternative is you have 2 choices. So it either looks like on the left-hand side or the right-hand side. This isn't a complete representation. This is only short snippet. In terms of just to make sure that I haven't put you all to sleep yet, do you guys have preferences for which code would you rather inherit, or if you were to come into a code base? You can say right side. Got some votes for right. Anyone for the left? Right, some people on the left. Cool, a little split. That's nice. And then what if I told you that, like, hey, look, the right-hand side, everything's unit testable, documentation friendly, right? Whereas the left-hand side doesn't really have these things, and so on the right-hand side, you could reuse the functions as they're kind of written, but on the left-hand side, you'd have to kind of refactor. Maybe you'll just cut and paste. Does that change anyone's perspectives? Yep. So the right-hand side is effectively Hamilton. So I'm going to describe and talk about it, but effectively the idea with Hamilton is trying to help standardize how you describe work, and you can use it for data, machine learning, LLM, and kind of even web workflows. I'll get into this, but effectively Hamilton has this nice duality between, if you can draw a directed acyclic graph or some sort of flow, you can kind of get a visualization. So you're always going to have this nice duality between understanding code and having something visual. So at a high level, effectively going to be talking about this applied to feature engineering, but this is kind of the things that I kind of want to impress on you is code cleanliness, quality, and coming into a code base that you don't know. So to motivate, why was Hamilton created in the first place? So let me walk you through the situation as it was at Stitch Fix. there was a data science team that was tasked with forecasting, operational forecasts for the business. The business would make decisions with these forecasts. So, for example, how many warehouse workers should we have given the expected client demand, right? But the world moves, and so does time. Marketing campaigns, stop and start. They could drive different, client traffic, and so their pipeline for these forecasts kind of look like the following, right? You get some actuals, they featureize it, fit models, and then predict the future and do something with it. Because of so the biggest problem in terms of this pipeline, wasn't getting it set up initially. It was actually iterating and say adding more features and dealing to make better forecasts. And so this is what Hamilton was set out to solve, was to really help them streamline and make the problems that they had with dealing, maintaining, and creating kind of features, something that basically remove that pain point for them. So to ground that, let me show you some code. I'm going to go through some pandas code, and I'm going to assume people here know Python. But effectively, the script that was kind of the code that was in this kind of featureized part kind of can be characterized in the following way. There was some, the initial parts of the code was to load some data. So this would be a kind of actuals. Then potentially, maybe based on configuration, there would be different code paths, right? So, Stitch Fix used to operate in the US and the UK, so there are different features that might be required because they have different holidays, right? Then there were people would write kind of features as one-line incantations, right? Maybe they would then add, basically they're adding to a data frame that would these features, and so maybe they would also delegate these things out to functions, right? And then at the end of it, they would come and save this data frame to some location, so then it could be picked up for the next step to do model training. I want to say this script looks pretty nice. It's short. You're like, what's the problem, Stefan? But I want to say, pictures the passions of time. People are going to come and go from your team. Invariably, with machine learning and kind of work and feature engineering in particular, you're generally always adding things, right? And so things are only getting to get more complex and more sophisticated. So you're always doing append, or like you're just adding to the code, really. You're very rarely removing. And so if you were to come to try to update, change, and say, if the world moves and something about the schema of this changes, right? How do you be confident in the things that you're doing? Well, if you are dealing with code that kind of looks like this, it's maybe easy and quick to get out, but like there is no unit testing or integration testing story, right? So if I was to change a particular feature definition, how do I know I haven't kind of broken anything very easily? Well, it didn't start with tests, so therefore it's kind of hard to add tests. And then this impacts data quality, right? So like, where do you measure? Where do you put the checks in, etc. You might have some, like code readability and documentation is hard to stick in here. So you're a new person, you're getting a wall of text, right? But in terms of why is average through expend or the three number important, right? There isn't really a great place or standard place that you can kind of document this, right? You could do inline documentation, but then it's not really I want to say done in a standard way by everyone. And then as the script kind of grows, as the things get more complex. So how do you actually understand the dependencies of, the first part of the code with the last part, right? You don't know that unless you've read the entire thing and kind of known it kind of end to end and intimately, right? And so if I was to change acquisition cost, like I would have to know that, oh, look, there's an assumption. There could be an assumption in multiply columns that, acquisition cost is, has some sort of shape, right? And so I could potentially impact, break spend B without really knowing it because, I thought I was just touching something independent, but then, I didn't actually know who was using it downstream. In terms of, iteration, right? So usually, you get something to production, but then you're iterating, right? So then, it could be you want to create another pipeline for another, type of model or something, or maybe you're doing some modifications, you're tweaking things. Ideally, if there are things that are common, you should be sharing them, right? And so there's less maintenance cost involved. But if you write code in this kind of a style, right, then the luckiest and the easiest thing is just to cut and paste. But then that proliferates, definitions of things. So then if you're given an output and you're finding something, you're like, where is the code that actually computes this, right? There's now several places where this could come from potentially, right? And so the code in this style isn't amenable to being reused. And then this naturally kind of impacts kind of onboarding and debugging. So at Stitch Fix, there were over 1,000 features before we brought in Hamilton. And so this effectively, it took a long time for someone to be ramp up to be productive and in a way that they didn't break things. And so so effectively to debug, the people who could debug the code base the quickest were the most tenured on the team. Right. And so as this kind of grew, things kind of got worse. So question for you. Are any of these pain points familiar to you? If so, which ones? Feel free to, type into the chat. I don't know if you can actually unmute, but if you want to say, that's also fine. But just curious, does this resonate? These pains resonate with anyone? Got one, yes. Reusability is one. Yep. Yeah, reusability. Yeah, lack of interest. Great. Yeah. Would you want to inherit code that was like this? Like, would you be in anguish if your colleague suddenly just left and you're like, oh, your manager's like, hey, now you're owning this, right? Yep, it's a good comment. Yeah, hard to read other people's code if documentation isn't clear. Anyone else want to add before I move on? Cool. So let me explain what Hamilton is. In one sentence, I would say it's a micro-orchestration framework for defining data flows using declarative functions. So that's a mouthful. I'll unpack that in the next couple of slides. High level, as I kind of alluded to at the beginning, you kind of get these nice software engineering best practices of everything being testable, documentation friendly, and it has this great modularity reuse story. It's just a library, so it's not a system. All you need to do is just be able to, you can install it in any Python environment. If you're bored of me and you want to play around with it in your browser, you can go to tryhamilton.dev. So let me unpack that sentence. So what do I mean by micro-orchestration? Well, the contra is macro. And so macro orchestration in terms of machine learning and kind of feature engineering, generally, I'm referring to things that handle the entire pipeline. So the macro, the high level. So Airflow being a macro orchestrator, something that you can use to schedule a different sequence of computational tasks that are strung together. Or maybe you're using dbt, for example, as well. So macro is like, how do I orchestrate this thing end to end and get the computational units running on different resources, right, and scheduled? Micro orchestration is smaller, so focusing on like the innards of what's happening in one particular step. So specifically in the context of say Airflow or dbt, it is focusing on what is the code that is actually being run in that particular task. And so Hamilton's focus is on that part, like trying to help make sure that that is the easier to iterate, understand, and debug. Since at Stitch Fix, in the case of that particular team, the macro was not the problem. It was the micro and being able to iterate and constantly change things in tasks without breaking things downstream. What is a data flow? It is just a fancy computer science term for saying how data and computation flow. And the main point is it can be expressed as a directed acyclic graph or a DAG. And this is where, DAG from why I started the company called DAGWorks, because, I'm all about this kind of representation of things. So this feature engineering code here can be described as a data flow, right? Because we can actually draw, some nodes and then add edges and say, these are dependencies. So to compute spend per signup, I need signups and spend. If I want spend zero mean unit variance, I need, zero mean, standard deviation, and zero mean, spend zero mean requires spend mean, which requires, both of them require spend, right? And so this is, it can be, this feature computation can be expressed as a data flow or a directed acyclic graph. What do I mean by declarative functions, right? So when you're just writing regular Python code, and the Python function name effectively says or declares something you can get out. And the function input arguments, declare what the actual dependencies are required for computation. Yeah, I know. Yes, I can post the slides after the talk or provide them. So definitely you can use them as a reference. The interesting thing is that you don't run these functions directly. That's kind of what Hamilton does. But the idea is like you should be able to read the code and you understand what it does and what it needs. And the reason for this kind of way kind of came up with, I'm sure you're may be familiar with is that, hey, look, something's happening with a model and I need to understand what it is. So I need to go check, say, the training feature set. And so that invariably leads you to kind of look at some tabular data and go, okay, this feature looks funny. How is that computed? How easy is that for you to find the definition for that code, right? And so the idea with Hamilton was that, okay, given this output data frame, can we make it as easy as possible to, given that particular feature, find the corresponding code for it? And so the idea was that, everything should correspond exactly to one Python function. And then the idea was, well, if you can put it into a function, can we just make it, very clear and independent to understand what's required to compute things? So just to kind of repeat things, in Hamilton, the output, so for example, a column or a feature is determined by the name of the function, and the dependencies of what's required to compute it are determined by the input parameters. So let me show you that in code. So instead of this kind of procedural way of kind of creating a feature C from summing A and B and a feature D from transforming C, you would rewrite that into Hamilton into two functions. So we would, given that these are potential two outputs that we want, we would write two functions called C and D. And then in terms of what's required to compute them, we would specify like, look, hey, this C needs A. And so we'd write that as function parameters. We'd use the body of the function to do the regular Python stuff that we need. And then for D, because it only requires C, right, we would just specify that as a dependency. Now, A and B are transitive dependencies, but with Hamilton, the idea is that Hamilton knows that to compute D, it requires C. We know then what C is, and we know that C requires A and B. So that's kind of the magic of Hamilton is that it will stitch together, figure out how to compute things. So specifically, a full hello world example is that you write these functions that define this kind of data flow or set of feature transformation processes. You then have to write some what we call some driver or code to kind of run and execute this. What you're doing is you're importing Hamilton, but you're also importing this Python module. You're then constructing a driver which constructs this directed acyclic graph representation by you pass in this module. It will crawl these functions. It will create if for each function effectively becomes a node, it will then determine the edges between things, and then you ask Hamilton like execute, give me these features, right? And so then Hamilton will understand that, hey, what outputs you want, and then will understand, it can walk the graph to understand and only compute the paths that are required to kind of compute the result. So rather than having a script where if you want to test one thing or you only want to get some subset out and you have to run everything, like with Hamilton, like you don't have that because Hamilton can figure out just the code paths required to compute the features that you are requesting. One thing to note is like, this example and what I've in this talk, I'm going to focus on pandas here just because I think that's a very common tool, but Hamilton kind of works for any Python object type. So these could be polars, data frames. These could be NumPy arrays. This could be your own custom object types. And Hamilton also works with PySpark as well. So in terms of just in general, when should you consider using Hamilton? Well, if you can draw a flowchart or a directed acyclic graph, Hamilton's you can put it into Hamilton. So feature engineering is kind of Hamilton's roots, and so that's the focus of the talk today. But just to kind of anchor and just give you, there are many other places that you can use Hamilton. So if you're tired of managing scripts, or you're building end-to-end machine learning pipelines, or if you have web requests, you can kind of use Hamilton there. Or even LLM workflows. So if you've heard of a tool called LangChain, Hamilton, you can actually use Hamilton instead to express the going to OpenAI and transforming things. Or if you're a code and software best practices enthusiast, then I want to say Hamilton's going to decrease your code complexity by helping you structure and chunk your code in a way that makes things much simpler to maintain and manage. But focus of the talk today is feature engineering. So and then just mentioned, Hamilton has been around for a bit, so I'm not going to show all the breadth and possibilities of power features and the things that you can kind of do, but suffice to say that you can kind of annotate functions with different functionalities that can kind of expand its breadth. And then I won't touch on it, but Hamilton does have plugins to make it easy to run on DBT or scale onto Ray or Dask or Spark if you know those things, right? And so one of the things to note is Hamilton is very portable as well. In terms of Hamilton adoption, like there's a lot of companies who are using it in production, so you wouldn't be the first. You'd be in good hands. It's pretty production grade. We did have to fork the repository from Stitch Fix because that's where it originally was. But suffice to say, we've got almost 300 people in our Slack community. So if you need help and you're using Hamilton, there's a community that can help. And then otherwise, otherwise people are using it for not just feature engineering, but also various other purposes. So onto feature engineering. So how do you use Hamilton for it? Well, just to give you a bit of a picture, so at Stitch Fix, we brought in Hamilton, and effectively that team grew from managing 1,000, just over like 1,500, I think, or 1,200 features. The team, in the course of a couple of years after, was managing close to over 4,000 feature transforms in a single code base. The team loved it, and effectively, they could add more features, and it didn't slow the team down, right? And effectively, actually enabled them for their monthly feature engineering kind of model fitting update task. They used to take someone a day to do it, to be confident to push something. With Hamilton, because we simplified the process and made it easy to be confident, it took less than 2 hours. It was then, therefore, easier to onboard new team members because you had lineage and always up-to-date documentation. Code reviews are faster because everything was, standardized in a way of like understanding, hey, you're going to change this, it's going to impact that, right? And then if you want to test and you wanted to do things, you could really easily test it. I'll kind of show examples in a bit. And then obviously there's plugins with documentation that you can kind of, if you understand Sphinx, you can kind of, the code that you write is also generally pretty amenable to Sphinx documentation. So at a high level, feature engineering with Hamilton is that you write, effectively, you need at least two Python files, right? You can have more than one Python file that describes your Python functions, but effectively, you got to write something that loads and transforms data, so your feature engineering code. You're then going to write this kind of run.py and instantiate a driver that's going to interpret the functions that you write into a graph, and then you're going to request what you want from that graph, and Hamilton will only walk those paths to kind of create a data frame. In terms of visually, pictorially, to kind of expressing that, right? So with Hamilton, your data lives somewhere in some sort of table, so it's very common, therefore, to write functions that extract from that SQL table or from that Parquet file. You're then writing these functions here that are then you're declaring the functions and their dependencies, so you kind of build this kind of directed acyclic graph. And then you actually can then write multiple run.py functions that express or use different parts of what's kind of defined here to actually materialize and create a different data frame. So so this is where you can actually start to build up this kind of feature catalog of sorts, right, of a superset of things, and then only for the particular context that and only compute things for the particular context that's required. So in the case of, say, Stitch Fix, it'd be that have one different context for US features and another context for UK features. And then in terms of how this impacts the code, right? And so effectively, by forcing you into this kind of a paradigm, this way of thinking and organizing things, a natural structure kind of emerges with your code base, right? So features, actually, you end up grouping features into thematic modules. So, or the marketing spend features, or the user features, right? They all kind of start to be grouped into similar modules, right? So then it's easier to create, find, kind of update, or even swap out. And then because you're not tightly coupling these definitions with where things actually run, right? It's actually then easier to kind of reuse things, or like, hey, if I have a different setup for development and production, it's easier then to kind of manage and maintain these things. And so therefore, even if you work in a handoff model with data scientists handing off to like engineering, this is actually pretty amenable, because if the data scientist kind of ends up writing Hamilton code, then it's very easy for the engineer to make heads or tails and wrap it up and kind of use it for that particular context of where things actually run in production. And so, great insight, Eileen. Yeah, I want to say, onboarding onto existing projects that have hundreds of features is hard. And so, this is where, Hamilton was kind of built to kind of help manage and maintain that structure and make it easy to, if people leave or new people come in, it's easy to understand and make heads or tails of what's going on. So what are the benefits of using Hamilton? So here's a function you kind of haven't seen before. I'll have links at the end, Alice, so you can definitely take pictures and things. But we have a lot of documentation stuff. So in terms of one of the things I think that to make code amenable and useful is like you got to have some testing documentation story, right? With Hamilton, it's kind of the functions that you write, because they're decoupled from where things run, you're effectively forced to kind of inject like all the things that are required. That means it's actually really easy to unit test, right? And so in which case, writing unit tests, so code is always unit testable, right? And so therefore, if you want to test something specifically, it's Hamilton set up to kind of, you didn't have to think about it, right? Because you're forced to kind of write things in this way. But then, oh, look, as a byproduct, everything is great, has a great unit testing story. Integration testing as well. So if you want to just compute a particular path, right, Hamilton allows you to kind of write integration tests or, just to test a particular path. Usually you would have to spend a lot of feature engineering time, or like you'd have to run an entire script to test one subset of it. With Hamilton, that's not the case. You can also add, runtime data quality checks pretty easily. So in the case of, so we have an annotation you can add that you can kind of specify some sort of expectations on. If you're familiar with another open source project called Pandera, Hamilton, which allows you to define, say, a schema. Hamilton also has a way that you can plug that in so that when something runs at runtime, you can validate that like the output actually matches your expected schema. So you can catch and validate things easier. The benefit here is that this is all tied in one place in the code. This isn't a separate system. You might have heard of things like Great Expectations or something like that. Hamilton is just, it's just compressing it, shifting it left, and like moving the expectation to be close with the code. And then it's self-documented, right? And so you can kind of, because these functions are outputs you can get out, you invariably name them things that are human understandable and readable, right? It's a little more things to type, but then the outcome is that you read code more often than you write it. So then it's easier to come back and go, okay, I understand what this thing is because it's named, similar. It's named the same as the output, right? And so you have this natural kind of self-documented code. You have the ability to use doc strings now. So if you actually want more documentation, you have a very standardized place to put it. And then we also have these annotations. So you can actually tag functions with more information. So if you wanted to understand, who the owner of this is, or does this have PII, like you can tag things with appropriate kind of information, and then you can visualize it. So I'll show that on the next slide. But effectively, I think with just these, test and grade these set of properties here, it enables you to kind of, I want to say, scale the team and your code base more easily than you otherwise would have, because you would have to, really think about the software engineering practices and principles to kind of do this. But with Hamilton, it's like, it forces you to write code in the way that this naturally kind of comes about. So visualization, as I said, is first class. Question from Alice. When using Hamilton, you need to define a function. So with Hamilton, the idea is Hamilton will figure out how to call which sequence of functions in the right way because of the way that things are, because of the naming. So to compute height zero mean unit variance, Hamilton will know it needs to find either another function, height zero mean or height standard deviation, to be computed first, or if it doesn't find a function, it will expect it as input. So that's how Hamilton figures out, how to compute things. And so you don't have to do anything. All you have to do is declare these functions and making sure they have the right dependencies for them to be computed. So visualization is first class. So if there's code that's running in production, you can always draw a picture of it, right? And so usually your documentation is always out of date. And so in which case you can build, something into your pull request or CI process or something to generate an image and place it and have, documentation that's always up to date. And so this effectively means like the code that you write actually encodes the lineage or the provenance of how things are computed. So what you're seeing here is a machine learning pipeline on the Titanic data set, but you can kind of see here that you can kind of see the lineage of what's required to create a training set. You can kind of see what features, what derived features were kind of created, right? And so this is where, Hamilton, someone new, or maybe even you're debugging and you're trying to understand, what connects with what. Like it's very easy to get this high level picture and then walk through it. And so in terms of, reusability and say, thinking about, okay, dev to production, right? This is just a Python function, right? There isn't anything special about it, right? And so this means this code can run anywhere that you run Python, right? And so you can, develop and run stuff in a notebook. You can run it in a Python script. You can put it into an Airflow task or, Array or PySpark or even, some sort of Python web service. And so this means that like the functions or features that you write are very portable. And so say you have an offline system, you can write functions there and then reuse them in the online system because Hamilton gives you that ability to A, reuse them, but then B, forces you to put them in a way that's, into a module that is actually facilitates reuse in the first place. And so definitely have a bunch of blogs here that go into more detail and depth as to like how you can write a feature once and kind of reuse it in multiple places. Also, for those who are using PySpark, there's a specific kind of we have a blog post on that. But just to kind of let's compare the code from earlier, right? So in this earlier code, right, this didn't have a great testing, documentation, visualization, or lineage kind of, or even portability kind of story, right? And so what would this code look like in Hamilton? In terms of, so I'm going to, I guess, walk through the first half, right? So one of the things you can kind of see is, this isn't all the code. So Hamilton is a little bit more verbose, right? But everything now is in functions. In terms of, say loading data, like one of the things you want to do is we can kind of specify a check output to ensure that, hey, the schema is what we expect. So if something was to break or change in the upstream schema, we could, fail early and catch it and ensure that like, hey, we're not going to compute bad features because our expectations change. We can then also, we're forced to like, if you want to do things, so Hamilton allows you to think in columns or data frames. That's kind of up to you. But for features, it's very easy. It's more natural to think in columns. And so you can then, actually explicitly say, hey, with load actuals, we're actually going to expose a few of these like raw features or raw columns so that then we can actually do computation. So it's easy then to kind of read this and go, okay, I understand what's being used from it. You can kind of see here that in the prior code, we had this if-else condition. And so if you start to have lots of if-elses, it's kind of, you have to mentally keep track of, what is the configuration and therefore what is the behavior. In Hamilton, you can pull this up to the top level. So we can actually conditionally create features based on configuration. So if I'm doing things in the US or the UK, right, I can write very specific functions. So then this means that this function can have different dependencies. I can unit test it independently, right? I don't have to deal with, worrying about configuration because this is kind of the framework kind of will pick the right one based on the inputs that you kind of provide. And then in terms of, magic numbers or average through expand, like we actually then, we have an actual function docstring where we can actually, specify or annotate like 3 weeks is important because that is the average something time in the business, right? And so, so now we have a standard way that we can, place documentation and kind of describe things where appropriate. The rest of the functions look pretty simple, but it's always very clear to understand specifically like what a feature is required and what it kind of depends on. And so therefore, if you were to change something upstream, it's very then easy to find what depends on it downstream, right? And so this code, therefore, then is, I want to say, an order of magnitude easier to maintain and manage. Maybe, it's a little more verbose, but then, the payoff is in the iteration and reuse down the line. And so then, just to somewhat comparing the code from earlier, is like one is we can actually, everything's unit testable as it wasn't before. Everything's documentation friendly. We can have the doc string, right? Lineage is clear because you can understand the dependencies of what things are kind of required. And then you can kind of get this visualization on the right? And so you can then easily and clearly see like, oh, I didn't have to so if I would manually be drawing this picture if I was trying to understand this code, but this is something that you kind of, this picture you kind of get for free with Hamilton. And then the code is reusable, right? It's in a module, it's in a Python module. It's a known construct then to be able to kind of reuse it and, in different kind of contexts. And therefore, I want to say this will be, you'll have a lot less headache maintaining this code than you would the other one. And the cost to kind of do so in terms of development, I wouldn't say is actually that much more, right? And so writing these functions isn't actually all that, that much more of an overhead than writing kind of that script-based form. And then, as I mentioned earlier, Hamilton's not just for, feature engineering, but the cool thing is that you can actually, start to make, break things up into bigger Lego bricks. And so it's very then easy to write a whole machine learning pipeline or some sort of LM pipeline where different Python modules describe different parts of your ecosystem, right? And so then it's very easy then to kind of compose and actually, so start small, start with feature engineering. And then if you want to expand it, right, you just write more, Hamilton kind of modules to either side to connect your directed acyclic graph. And so, so in which case it's then Hamilton's very lightweight, so you can just start and just use it for feature engineering. But then, if you want to do more with it, you can. If not, you don't have to. And then there isn't really much of a downside because you're just still writing regular Python functions. So if you have some other context, you can still use those Python functions, however you would normally use, a Python library, for example. So I'll get to questions in a sec, but otherwise, in terms of a quick recap of this talk, so I could easily talk for much longer into the depths and details of Hamilton, but if for me, feature engineering with Hamilton, to summarize, Hamilton it's a very lightweight library, right? That you declaratively can express these kind of transforms, which are the bread and butter of what you do for feature engineering. And then high level is write code that people aren't terrified of inheriting. So this is where my thesis is you could give Hamilton to your intern, and they could write production code, and then no one would be terrified of inheriting things when they leave. The paradigm, so because Hamilton forces you to write code in a certain style, right? It is kind of like a paradigm. As a byproduct, you get these software engineering best practices, right? And I think this actually increases the value of your work, right? Because it's easier, A, to understand features. Everything is, again, testable, documentation friendly. You can draw a picture. You can reuse these features. So then things are more reusable, portable, and modular. So if you need to make a change of just a specific thing, like which function to change it on, where it is, and then you can identify what it impacts. And effectively, it does this because it standardizes the way that you kind of write code and iterate on a code base. And then it is lightweight, runs anywhere that Python runs. So this means that you can, develop wherever you develop Python, and then reuse it and deploy it wherever in production that Python code needs to run. And so this means actually, depending on different companies, different setups, but this is actually Hamilton can provide a pretty well-defined kind of interface for, say, a data science, even a data eng team to operate, or a data science and machine learning team to kind of collaborate, because functions are all standardized. Everything's can be done expressed in modules. So then it's then easy for teams to kind of either inherit, delegate, or kind of reuse each other's work. Just a quick note. So I'm trying to also, I'm starting a company, and so the one thing that I'm adding on top of Hamilton is that if you need better handling of versioning, lineage, catalogs, and observability in terms of what's created and what the code is running, I invite you to sign up for free and try it out. DAGWorks.io. You do have to be using Hamilton to make use of this, but otherwise I would love feedback there. But otherwise, at the end of my talk, thanks for listening. Definitely, I'll make these slides available. There's also a bunch of different links and content and documentation that get you on your Hamilton journey. And then otherwise, I will go through the Q&A now. So thanks, everyone.
Thank you, Stefan. The journey was wonderful to hear about the development of Hamilton. So here we have a set of questions. Can I post your questions to you?
Yes, please.
Yeah, sure. So one of our associates says Hamilton sounds amazing. She has two questions. One is, how was your journey of developing Hamilton as a CEO happen?
Yeah, I mean, so thankfully, so we developed Hamilton back at Stitch Fix, right? And so definitely got, you could say, good feedback from the users there. And so when we decided to open source it, a bit of a thesis was that, hey, it's a bit unique and it's a bit of a different thing. And so Hamilton's already had impacts on other frameworks in terms of trying to provide a declarative way to kind of write things. And so Dagster being an example that took inspiration from Hamilton for some part of its feature set. But otherwise, the main friction I think we find with Hamilton adoption in general is people are a little afraid of how does this actually change how I write code? Because everyone likes to develop things in their way, and so not too uncommon friction. And so a lot of it is just giving people the time to actually, and the examples and the documentation, and this is where I need to actually create more videos, I think, some more video content, but to make to show people that it's actually, the activation energy is actually pretty small. There is a little bit of how do you frame and think on certain aspects with Hamilton, but we're always trying to improve documentation there to make that something that is easy to answer and to show people no, this is possible, and this is how do you kind of do it. But that is the main feedback you could say with Hamilton is that I like it, but how do I get my colleagues to adopt it is something that we encounter, in which case we have I want to say a lot more documentation and content there that can help you champion Hamilton if you want to win over your colleagues.
Actually, that is what was following up with her question. She also asks, what are the different types of feedback that you got from the clients? Like, how did you pitch your
Yeah,
product and the different type of
yeah. I
feedback?
mean,
Yeah.
yeah. So like in terms of if you think most teams to be more efficient, they need to standardize, right? And so invariably, I think there's a little bit of like data science work is generally started by very technical, very like machine learning, data science, are very technically adept people who generally actually, because they come from say PhD backgrounds, are very actually great at working by themselves. But then in terms of longevity for code, it's actually a team thing, right? And so this is where trying to frame things as Hamilton being the way that you can help standardize things without having to write and manage your own bespoke custom feature catalog or way that you express features. It's kind of the way that would be thinking about it. But that is like what I want to say. If I was to talk to a manager or someone, or the head of data science or machine learning, that's kind of that story resonates. And then because with LLMs now, you can also apply Hamilton not only to data, machine learning, but also LLM stuff. It's also the feedback is like, yeah, one tool set or one way that you can describe things that express the DAG is then helps standardize, makes things more efficient, and the team has then a shared common language to speak on. So that is the pitch that resonates with people. But the harder part is the implementation, getting people to to change their ways a little to kind of adopt, since um, uh, some people like to engineer their own constructs because they find it more of a challenge. But this is where I think over time, more open source standard. That's why you should use open source, because the standards can live for a lot longer than what you potentially could come or construct in your own company, unless you're a big tech company like Google or someone who will always invest in their own kind of platform code.
That's definitely true. Like following up with this question, I would like to also understand like what is the business value that is being added? Like, could you quote a
Yeah.
value?
So productivity is hard to manage. So this is where most data teams don't know how to measure themselves. So if I was to tell you, hey, I can make you 20% faster, like it's hard to say what value that is to your business depending on your work, right? And so in the case of production code, if you can quantify it in terms of how fast does it take to debug or resolve things if they're fast, so that is a quantifiable cost that you can kind of measure of like how much people human time. The other is how many iterations can you get out, right? And so can you then estimate like, well, if we can build better models faster, we'll come and find something that lifts the business sooner, right? And so then that is the kind of spreadsheet modeling you kind of need to do to show business. But at a high level, I think this Hamilton enables data science people to kind of or at least people who depending on how your company operates, to do more of the software engineering work, because it's a simpler paradigm. There isn't anything to do. So in which case, it's easier to, you could say, write more code from the person who's developing it. And so, so to me, it's like we can make things more human capital efficient. So one team is more, it can do more. So therefore, you can potentially, you don't have to pair quite as much engineering talent or support to get something to production, right? Because if everything's standardized and the whole team standardizes it, then the engineering support has everything already standardized for them, and then you don't need quite as many of them to help support the team. So it's along so the open source side is all along trying to make teams more efficient and more human capital efficient by giving a standardized kind of way to do things. It's a good question, but like hard one to answer for each team though.
Yeah. Okay. So do we follow any coding standard over here? Like Hamilton seems to be like a Python framework. Is there any coding standard which was taken as a reference and then developed on top of it, or is that?
The main task was, can we make things unit testable, documentation friendly, and so you could understand what connects. And so Hamilton, I'm a computer scientist by background, and so in which case for me, having a great operational story or a software development lifecycle story is really kind of what drove the design goals of Hamilton. And so that's really I want to say there was no framework that inspired me, other than I wanted to keep things simple, because I believe Python functions are really great. You don't need much object-oriented code in the data world in terms of defining transforms, and so functions are pretty well contained. And so, in which case that was really you could say more functional thinking, if anything, was trying to drive some of the things of Hamilton here, but without you having to buy into a full functional paradigm if you have experience there. And so that's kind of yeah, what I took inspiration from to kind of, help design and build Hamilton. So I see there's a question from Rebecca. When doing feature engineering, we often try to automate the features testing. Should this feature be divided by 5, 10, 10, or 100? Can you explain how Hamilton can be used in these situations? So Hamilton has the ability to parameterize a function. So you can kind of, in that case, you can create different features that one would be divided by 5, 10, 100, right? And so you could create a superset of all possible things. And so then determining whether it's useful or not is up to you because you have to build the model and kind of measure it. But at least with Hamilton, you can kind of structure it in a way that you can easily kind of create and add these features. And then I guess if you really want to delete code, Hamilton can give you the impact statement, or at least you can easily figure out what you're going to impact. In terms of base pipeline and kind of grid search for sklearn, for example, it kind of Hamilton, the one thing to wrap your head around Hamilton is like what level you're kind of thinking in, right? And so you can think of one directed acyclic graph being one model fitting kind of run, right? But Hamilton does have constructs where you can kind of parameterize a graph, right? And so if you know the grid and the search you want to do ahead of time, you can actually create a whole parameterized graph that then Hamilton will go and kind of compute for you. So that is an extremely, I guess, that is a great question. And so this is where I'd say reference documentation. But suffice to say, there's a few ways to kind of approach kind of what you're doing. And then depending on where you're computing, there are hooks there to like, hey, I want each of my grid search parameterizations to run on Ray, right? And so Hamilton does have constructs to do that, but you have to. The main question is depending what are you optimizing for is part of like the way that I think is to like how you'd set up in Hamilton. But suffice to say, I want to say yes, you can kind of to do that and do that in a structured way. And if that didn't make sense, Rebecca, do feel free to ask again or ask a clarifying question.
We'll jump on to the next question from Alice. She has a part of code which was shown in the slide, and she wants to ask, what's the purpose of adding PD series? Is it required?
Yes, a good question. So I didn't touch on this. So Hamilton, code example. So with Hamilton, you actually you have to type annotate the inputs and outputs, because Hamilton will do a lightweight, when it constructs the graph to make sure that like, hey, these things are the same types or at least compatible types, and they're not going to conflict, right? And so, which case, if one of these end up being a data frame and I think it's a series, right? Hamilton was like, hey, you actually can't construct this graph because your types don't match. So that is kind of how Hamilton is using types. We actually have some, we're looking to expand the type kind of system. And so in which case, if you wanted to annotate more expectations on types, we can then also use that as a way to kind of do input and output type checking. But that is really, like I think aids in readability as well as to kind of, why you have these type annotations. And so Hamilton helps kind of therefore make sure that the graph is constructed and then gives us an avenue to then do more sophisticated type checking at runtime as needed. Good question, Alice. Anyone else have any more questions?
Yeah, I have a question. From the session, I understand like Hamilton is quite useful not only for time series forecast, and also it would be helpful for the unstructured data. Like, could you explain more about it?
Yeah, I mean, so if you can draw, a set of processes that you want to take your data and transform it, right? And so with Hamilton, you can directly model that as different functions and then different dependencies, right? And so any Python object type, any kind of data type that you can kind of model in this way. So that's why you can do web request kind of modeling with Hamilton. That you get a web request in, you want to take the data, transform it, maybe go to a database, pull something out, change it, do a prediction or something, right? Hamilton, you can kind of, if you can describe it as a directed acyclic graph, you can kind of put it into Hamilton and run it. Do you have a more specific question there, but that's the high level kind of way that I think about it.
That answers my question. Could you say more about the cost of maintenance? Like we just touched upon the topic, but we did not elaborate more on it.
Yeah. So, so in terms of maintenance, right? I think in terms of the way that I'm interpreting the question is, people come and go, right? There is, I think in my, the world moves, right? If you have something running in production, like say data moved, or hey, the product now has a new set of client features or inputs, and these old ones are deprecated, and I need to go update my pipelines, or something along those natures. Kind of generally what how I'm interpreting maintenance, right? The one thing that with Hamilton that you can do is like, because you're grouping things into Python modules, right? Hamilton actually gives you a very easy way to kind of add, change, or update, or switch them out. So, for example, if you are moving moving databases or something, right? The idea with Hamilton is that the only functions you'd need to change would be the data loading functions, because they're the only ones who are coupled or dependent on like what database you're using. The downstream features shouldn't care they're decoupled, because all they need is the right data with the right type to kind of satisfy and kind of run things. And so in terms of maintenance, one of the things is like Hamilton enables you to more easily then to like be very surgical with what the change is, or like swap out an entire module for a different one, right? And so that's where that is. In terms of testing, you can build a CI or continuous integration pipeline that when things run, you can obviously have all the tests and integration tests you want, right, to help make sure catch and make sure that things don't break. Yeah, that's kind of the high level of what I see Hamilton helping facilitate with maintenance, because say there's an issue and you need to debug it, right? Then at least you can more easily trace or understand like where things came from and how things connected. So then it makes discovery of what needs to change easier. And then if you need to add more expectations, and this is what I was saying with like the check output annotation with schema stuff, like you can actually add that in. So then next time you're catching it early, and therefore know exactly like what changed or what has changed that then you need to either go talk to another team to fix, or fix the code yourself. Does that make sense?
Definitely. This visualization is quite interesting. Actually, we do this tree whiz like kind of thing for understanding the feature, like dissecting the feature and understanding it to do a feature engineering. Now, I mean, on an alternative path, this is quite interesting to know about the feature, like where it is placed and what are the dependencies for it, and with which we will be able to do feature selection at a better way, I believe. So, consolidating. Yeah, please.
Yeah, I was going to say, feature selection is just about like what is the data set you're creating, right? And so Hamilton gives you a few options to like flexibly kind of create and do that dynamically, right? And so then this means that when something runs, it's very clear as to what paths, what features. And then if you connect this with Git and you track the Git commit shard, then you also then have a very lightweight way to then like, hey, I did feature selection, and as long as you store the pointer of like what that state in the code is, you always then, assuming you have you store the source data in a way, you always then be able to go back and kind of recreate it as well. So it's then easy to as things go over time, understand and actually go back in time to recreate something if you need to, because as long as you kind of store with Git and track things, because it's all lineage as code.
Okay. So I have one more question. Like we were speaking about the testing and documentation part. Is Hamilton capable of generating automated code as test scripts?
We have an issue out on the repository to help bootstrap unit tests. So if you think about like these functions, and now and you want to write unit tests, like the boilerplate to write to set this up, like we kind of have all the details, right? So there is an issue open to kind of have a command line that can, given up some Python code, bootstrap unit tests. And then I want to say now with LLMs, you can actually, this is where, we can actually write an integration. So if you give the OpenAI key, it's on the, we could then potentially even help you auto-generate the first version or something of those tests, because, I mean, with Hamilton, things are pretty descriptive. And so this is a lot of context that you could potentially provide the LLM to generate tests for. And so definitely see, paths and things in the future that we can kind of more easily streamline the testing story.
Definitely. It sounds interesting. And we would be excited to hear more about your generative AI or LLM based approach that Hamilton has handled. Like if there is any story that helps us, please.
Yeah. I want to say if you're doing retrieval augmented generation, it's very easy to model in Hamilton of getting a document, going it through some processing pipeline of chunking document, going to a vector embedding and then putting it into a vector store. So I want to say that is a nice use case of Hamilton. And then, but otherwise, yes, if you're doing LLM stuff, I want to say, yeah, also take a look at Hamilton. I can definitely. We have some blogs as well that I can point people towards on. So if you go to blog .dagworks.io, you can kind of see. I wrote a one yesterday on kind of RAG ingestion, but we have a lot of different blogs on a lot of different topics. So if you're using IPython notebooks, we actually have a Jupyter Magic that can help you develop and kind of see Hamilton stuff. So I would say if you go to our blog and you don't find what you want, let me know. But like there's a little search button here that you can kind of search for things that have LLMs. So we do have posts on building in a modular LLM stack. So if that's also something of interest, there's definitely hopefully got content to get you started.
I think we can wrap up the session. We are good with the information that you've shared. It was quite informative and energizing for us in terms of its application perspective. Like it can go around from normal ML based application till LLM, so which is quite interesting for us to know. Stefan, we had a wonderful time with you, speaking about Hamilton and its perspective and different perspective that it can help us in bringing the scalability, deployment-based approach and the reusability of the code. I think we would have more hands-on session in future with you. Thanks a lot for coming into our session and giving us insights about Hamilton. Yes, your final thoughts.
No, thank you for having me. I want to say, yeah, if you like Hamilton, would love a star on GitHub. But otherwise, yeah, feel free to join the Stack community. You'll find me there. I'll say hello. And otherwise, yeah, it was a pleasure. Talking about this. So, thanks, everyone.